It begins, as so many cosmic stories do, with something that should have been routine. For more than a century, astronomers have sketched, photographed, and now digitized thousands of comets. We learned to expect a certain look, a bright core wrapped in hazy coma, one primary tail of dust curling gently away from the sun, and a straight, electric blue ion tail being pushed back by the solar wind. That is the comfortable picture that textbooks carry and planetarium shows repeat, the quiet assumption that frames almost every new comet image we collect. Then, late on a humid night in Rayong, Thailand, an amateur astronomer brought that picture quietly to its breaking point. A long exposure of the interstellar object known as 3I Atlas appeared on the laptop screen, grainy at first, then slowly sharpening as the software stacked frame after frame. The familiar twin tail pattern emerged, dust and ion, but something else refused to vanish into the background noise. A third structure, narrow and unnervingly straight, stretched in almost the opposite direction, not away from the sun, but toward it, as if some invisible hand were drawing a line straight back into the glare. Most oddities in astronomy die young. They are traced to camera defects, tracking errors, or tricks of perspective when Earth slices through a comet's orbital plane. Yet the more carefully observers examined the Rayong data, the harder it became to file this away as a passing glitch. Successive nights reinforced the same unsettling geometry. While the main tails behaved as physics would predict, that third feature seemed to sharpen and hold, a thin, persistent blade of light pointed into the very source of the radiation that should have erased it. The story you are about to hear is not a tale of alien armadas or secret engines hidden in the dark. It is, first and always, a story about physics, about how ice, rock, dust, charged particles, and light can conspire to produce shapes that do not fit easily into the diagrams we teach. Tonight, we will walk slowly through what the Rayong Observatory saw, through the known behavior of comet tails, and through the uncomfortable possibility that 3I Atlas may be revealing a kind of structure we have not yet fully modeled. And in the background, moving patiently outward from the sun, a solar storm prepares to test this fragile pattern in a way no human could design. Here, on Dreamy Stargazer, we treat images like the one from Rayong as invitations. With a calm voice and a patient pace, we turn them over like stones in a quiet river, looking for the patterns carved into their undersides. This is a place where you are allowed to be both sleepy and curious, where a documentary can double as a lullaby, and where even a stubborn piece of data from a small Thai telescope can open a door to a larger cosmic question. If you find comfort in drifting off while listening to distant worlds and quiet equations, you are in the right company. As you listen, you might let your own thoughts wander a little. You might imagine how many other observers across the world are watching the same object trace its brief passage through our sky. You might decide to join them more actively, to follow future images, to pause the video and replay a sentence that caught your attention, or to share a theory of your own in the comments once morning comes. If this way of exploring the universe feels like home to you, you can gently support it. You can subscribe so that new journeys into the dark find their way back to you. You can leave a quiet note about what you think the third tail of 3I Atlas might be. Or you can simply let the video run while you rest, knowing that others are awake under the same sky, watching and recording. Every small gesture helps this shared observatory stay lit a little longer. Now dim the lights. Imagine, for a moment, the observatory at Rayong as a simple, almost ordinary room. A modest telescope tracks slowly across the sky. A computer hums softly in the corner. Outside, traffic noise and the rhythm of human life continue as usual. Inside, a single person leans toward the screen as the image of Three Eye Atlas resolves, pixel by patient pixel, from a smear of motion into a distinct three-tailed form. It is not dramatic in the way a rocket launch is dramatic. It is quieter than that, a kind of intellectual jolt that begins with a small intake of breath and the feeling that something does not match what your memory expects to see. The first instinct in such a moment is almost always to doubt the machine. The observer checks the focus, recalibrates the tracking, inspects each frame for satellite trails or subtle streaks that might mimic a tail. They compare the raw image to processed versions, asking whether the software that enhances faint structures could be playing a trick. Then, with the caution built from many long nights, they check star catalogs and orbital data to be sure that the strange sunward streak is not a background galaxy or a passing asteroid pretending to be attached to Three Eye Atlas. As the checks clear one by one, the attention shifts reluctantly from hardware to nature itself. Comet researchers know that so-called anti-tails can appear when Earth crosses the orbital plane of a comet, making the dust lanes seem to point toward the sun, even though each grain is still obeying the usual forces. That explanation is the first refuge of a cautious mind. Yet when the geometry is reconstructed and the timing of the observation is compared with the object's path, a disquieting detail emerges. The cleanest predictions say that Three Eye Atlas should have shown such a feature more than 2 weeks earlier, and that by the time of the Rayong images, any illusionary anti-tail should have softened and faded. Instead, what the Thai images suggest is a structure that is not dissolving, but clarifying. Night after night, within the limits of weather and equipment, the narrow sunward feature looks more like a deliberate stroke and less like a smudge. It is as if the dust and gas near Three Eye Atlas are being guided into lanes rather than scattered into a fan, as if some additional rule is being written into the way particles leave its surface and respond to light and plasma. For a listener drifting toward sleep, it may help to linger on the picture rather than the equations for a moment. Picture 3 distinct elements. The main dust tail, curved gently away in a broad, soft arc. The ion tail, straighter and bluer, tracing the invisible pressure of the solar wind. And then this third element, a thin spear of brightness pointing sunward, apparently resisting the very forces that shape the others. On the screen in Rayong, they are just pixels, but they encode distances of millions of miles and timescales of many years, compressed into a single frame that asks, very quietly, whether our current story of comet physics is complete. What does it take for a new anomaly to be taken seriously in a field that has cataloged so many comets already? How many nights of confirming images? How many independent observers? How many careful checks against known illusions are enough before the community is willing to treat a third tale as more than an artifact? As the story of Three Eye Atlas unfolds, this Rayong Revelation will stand as the first act, a visual clue laid gently on the table, waiting for geometry, plasma physics, and time to decide what it really means. For as long as people have drawn comets, artists have been allowed one small liberty. Sometimes the tail bends a little more dramatically than the physics would strictly prefer, and sometimes a painter lets a streak of light point almost back toward the sun. In reality, that defiant geometry is rare. Dust and ions almost always stream away from the star that warms them. Yet there is one optical trick that nature can perform without breaking any laws. When Earth happens to slice through the thin orbital plane of a comet, observers can find themselves looking edge on at a sheet of particles that normally lies flat in space. In that special alignment, the sheet can collapse into a narrow, sunward pointing spike on camera, a so-called anti-tail that has startled and then reassured generations of comet watchers. Because of that precedent, the first attempts to explain the Rayong images of 3I Atlas leaned heavily on orbit diagrams. If this interstellar visitor carried a dense sheet of dust along its path, and if Earth had crossed that sheet near the time of the observation, then perhaps the third tail was nothing more than perspective, a flat structure seen from an unforgiving angle. The mathematics of this idea are not complicated in principle. One can picture a thin hoop of particles wrapped around the sun, with 3I Atlas tracing part of that hoop and Earth drifting through the same plane. If both worlds lined up just right, the hoop would compress into a thin line on the sky, apparently pointing toward the sun, even though every grain in it still feels the usual outward push of radiation and the solar wind. On paper, this solution is comforting. It lets the Rayong feature join a quiet club of rare but understood geometrical tricks, cousins of the anti-tail that made Comet Arend Roland briefly famous in the late 1950s. Those older cases taught astronomers to be wary of their own point of view. A comet can seem to sprout a strange sunward spike only for the effect to fade as Earth moves on and the sheet of dust is once again seen from above or below. No new forces are needed, no exotic materials, only a fortuitous crossing of paths and a willingness to remember that pictures flatten three-dimensional structures into misleading silhouettes. For a while, it was tempting to file 3I Atlas into that same chapter and move on. But astronomy is a patient science, and orbital mechanics is a stubborn bookkeeper. When observers began to check the timing of the Rayong images against the path of 3I Atlas, a different story emerged. The key calculation is simple in spirit. One asks, on what date did Earth pass closest to the orbital plane of this object, the imaginary flat sheet defined by its motion around the sun? If the anti-tail explanation is correct, the most dramatic sunward feature should appear near that crossing when our viewpoint is edge on. For 3I Atlas, that crossing did not line up with the Thai observations at all. It fell roughly 18 days earlier, at a time when the object was fainter and images were scarce. By the night when the Rayong telescope recorded its sharp, triple-tailed form, Earth had already moved on, tilting us away from the plane where such illusions are strongest. That mismatch in timing is what turns a comforting story into a restless one. If the third tail were a classic anti-tail, it should have been most striking when our line of sight lay almost exactly in the orbital plane, and it should have blurred or faded as the days passed and our angle changed. Instead, reports from Rayong and other sites suggest that the sunward feature grew clearer, not weaker, as the geometry drifted away from the ideal. It is as if a shadow grew darker after the lamp was moved, or a reflection in a lake sharpened as the wind picked up. The logic does not quite close, and for a field that relies so heavily on geometry, that is an uncomfortable place to rest. There are, of course, ways to soften the discrepancy. One can argue that the dust sheet of 3I Atlas is not perfectly flat, or that small uncertainties in the orbit solution might nudge the true crossing date closer to the Thai observations. One can imagine that instrumental sensitivity, sky conditions, or processing choices made the anti-tail easier to see on certain nights, even if the underlying structure was strongest and earlier. Grounded speculation allows some of these adjustments. The universe is messy, after all, and no simple diagram survives contact with real data unchanged. Yet each of these appeals to complexity has to pay a price. The more special conditions we ask for, the less the explanation feels like a general rule, and the more it feels like a delicate excuse. In the quiet hours, when astronomers compare notes across continents, this is the kind of detail that keeps returning to the conversation. A third tail that appears late instead of on cue. A sunward spike that seems to lean into an angle where perspective should be working against it, not for it. If you imagine the orbit of 3I Atlas as a pale ring in space and Earth as a small bead sliding along its own track, the moment of perfect alignment is brief and well defined. That moment appears to have passed, and yet the Rayong images show a structure that acts as if alignment has somehow been extended, as if an invisible hand is still holding the sheet of dust in place for us to examine. As you lie back and let these diagrams pass through your thoughts, it can help to remember that this is how progress often looks in astronomy. First, there is a generous application of known explanations stretched to fit an awkward case. Then there is a growing sense that the fabric is being pulled too thin. Somewhere between those stages, a specific question emerges. In the story of 3I Atlas, the question might be framed this way. If perspective alone cannot fully account for a sunward feature that sharpens after the best geometry has passed, what additional ingredient needs to be added to the model? Is it a different distribution of dust, an unexpected density, or a subtle influence from electric and magnetic fields that has not yet been fully woven into the standard picture of comet tails? Later in this journey, we will explore some of those possibilities more directly. For now, it is enough to hold the Rayong images in your mind as evidence that simple illusions do not quite close the case. The third tail of 3I Atlas behaves like an anti-tail that refuses to follow the normal opening and closing act. It appears late, lingers, and grows more sharply defined when the show, by all rights, should be fading. That quiet defiance of timing is the thread that will lead us from familiar geometry into the deeper territory of forces and structures that may be shaping this interstellar visitor in ways our current diagrams only begin to suggest. When you first look at the Rayong images of 3I Atlas, it is easy to be distracted by the novelty of three separate features fanning out from a single, small nucleus. But after the early questions about perspective and camera tricks have been set aside, another, quieter detail begins to stand out. The third structure, the one that points sunward instead of away, is not only present, it is stable. Night after night, within the limits of weather and equipment, it keeps returning with nearly the same orientation and a clarity that feels oddly deliberate. In a universe where most cometary structures behave like smoke in a shifting breeze, this particular plume behaves more like a carefully held line. Comet tails are often described in static terms, as if they were solid, sculpted appendages attached to a moving nucleus. In reality, They are more like constantly renewed weather systems. Dust grains are released, accelerated, and dispersed. Ionized gas is shaped and reshaped by changes in the solar wind. Even when images are taken just a day or two apart, the major structures can shift, fragment, or blur, reflecting subtle fluctuations in the environment. Astronomers who specialize in these objects learn to expect a certain restlessness. A tail that looks sharp and narrow tonight may soften or kink tomorrow. A jet that seems straight in one exposure might twist or fan out in the next. Variability is part of the normal language of these objects. Historical anti-tails, the classic sunward spikes produced by geometry, respect that variability. Comet Arend-Roland, which startled observers in the late 1950s with a striking sunward feature, did so briefly. Its anti-tail rose, drew attention, and then faded as Earth's viewpoint shifted. When the geometry that produced the illusion passed, the feature weakened and dissolved into the broader dust environment. Even at their most dramatic, these structures tended to be slightly diffuse, softer at the edges than the main tails, more like a faint lane in a fog than a rigid beam etched into the sky. They arrived and departed on a schedule that could be traced directly to the changing angle between Earth, the Sun, and the comet. The case of 3I Atlas, as implied by the Rayong sequence and supporting images, seems to bend that script. Instead of appearing and then dispersing on cue, the sunward feature seems to tighten. When frames from different nights are aligned on the nucleus and stacked with care, the main dust tail and the ion tail behave as expected, broadening and shifting slightly as the object moves and the observing conditions change. The third structure, however, does something different. Its edges appear to sharpen. The brightness profile along its length becomes more peaked. Instead of smearing into a wider fan, the light seems to converge, giving the impression of a narrow, persistent lane that is being maintained rather than merely glimpsed at a fortunate moment. This impression of convergence is part visual, part numerical. Measurements of the angle between the third feature and the line to the sun show only modest variation over multiple nights, despite the fact that 3I Atlas is moving along its orbit and Earth is advancing along its own. In simple terms, you would expect the apparent direction of a purely geometrical anti-tail to swing or soften as the viewing geometry evolves. Here, the apparent orientation clings stubbornly close to the simple sunward line, as if some local physics near the object is doing the work that orbital alignment usually does in other cases. The feature behaves less like a sheet being seen edge-on by chance and more like a guided plume that is being actively held in that configuration. Of course, data reduction can sometimes mimic stability where none exists. Astronomers are aware that stacking images, enhancing contrast, and subtracting background stars can create artifacts. To guard against that, they inspect individual frames, vary the processing parameters, and compare independent reductions from different observers. In the case of 3I Atlas, those checks, as they are reported and discussed, keep pointing back to the same conclusion. Whether the images are processed to highlight faint detail or to preserve only the strongest signal, the third feature persists. It may waver slightly at the edges, but its core remains distinct and linear, anchored to the nucleus in a way that does not feel like a coincidental alignment of unrelated streaks. That is why some researchers, even those inclined toward conservative explanations, have begun to speak not just of a third tail, but of a third channel. The language matters. A tail suggests something passive, dragged into shape by external forces. A channel suggests something more organized, a pathway along which material is guided or constrained. If the sunward structure of 3i Atlas is indeed that kind of channel, then its stability becomes a clue rather than a nuisance. It would hint at an underlying framework, perhaps magnetic, perhaps related to the way charged dust and gas interact near the nucleus, that can hold particles in a relatively narrow corridor, even as the object spins and the solar wind fluctuates. From a grounded perspective, there are several ways to imagine such a framework without leaving the domain of natural physics. A denser nucleus with a complex internal structure might produce vents that preferentially release material along specific axes. An intrinsic magnetic field, generated by a metallic interior, could shape plasma into filaments rather than clouds. Interactions between charged dust grains and the larger scale magnetic environment could encourage self-organization, turning what might otherwise be a messy plume into a disciplined strand. Each of these ideas stretches our current mental picture of a typical comet, but none of them requires us to abandon the core principles of gravity, electromagnetism, and thermodynamics. As you listen, it may be helpful to hold two images in your mind at the same time. One is the textbook comet, its two tails flowing neatly away from the sun, responding to light and plasma in familiar ways. The other is the Rayong version of 3i Atlas, with a third, stubborn line of brightness pointing back toward the star, maintaining its shape as nights pass and viewing angles shift. Between those two images lies a question that is both simple and profound. What kind of nucleus, what kind of internal structure or surrounding field is required to transform a transient anti-tail into a stable, beam-like channel? In the next part of this journey, we will begin to examine that question through the lens of energy and resource, asking whether a standard, fluffy comet could reasonably afford to power such a feature for long, or whether the very persistence of the third tail is quietly telling us that something about the interior of 3i Atlas is not as ordinary as we first assumed. When a strange structure shows up in an image, the first instinct is to ask whether geometry can explain it. Once that question has been pushed as far as it will go, the next, more demanding question steps quietly into view. It asks about cost. How much material must be lifted? How much energy must be spent for 3i Atlas to sustain not just one, but three distinct features, including a dense sunward channel that seems to resist the flow of solar radiation? In the dark, this question sounds almost philosophical. Under the cold light of physics, it becomes an audit, a careful balancing of gains and losses that can either support or quietly undermine our picture of a normal comet. At its simplest, the energy budget problem is about mass loss. A comet tail is not a painted ribbon trailing behind a solid object. It is a river of particles that must be constantly replenished. Ice sublimates, gas escapes, dust grains are dragged along and then let go. For many comets, rough estimates suggest that tons of material can be lost every second when they are near the sun. Those losses are spread out over broad, fan-shaped tails and transparent comae, making the depletion less startling. The nucleus erodes gradually, its irregular shape softened over successive passages, its more volatile components removed. The process is wasteful, but it is not puzzling. Sunlight provides the energy, and the changing face of the comet is the inevitable bill. With 3-eye Atlas, the shape of the bill looks different. The Rayong images hint at a third feature that is not diffuse and wandering, but concentrated and apparently thick. A sunward channel of dust and plasma, if it is real, implies a steady stream of material being forced into a relatively narrow lane rather than drifting into a broad plume. To keep that lane populated, 3-eye Atlas must lift grains from its surface, accelerate them into the local environment, and somehow prevent them from simply being blown backward like everything else. Each grain represents energy spent and mass removed. When you add up those costs over days and weeks, the numbers begin to press against what a small, fragile nucleus should reasonably afford. There is another complication. Interstellar objects like 3-eye Atlas are not expected to be large. Even if we grant it a nucleus tens of kilometers across, with a mixture of ices and more solid materials, the total mass is not infinite. If the sunward feature is as dense as the images suggest, and if it is maintained for a significant span of time, the implied outflow pushes comet models toward the uncomfortable territory. The nucleus would need to behave less like a loosely bound snowball and more like a compact, stubbornly cohesive body that can lose large amounts of material without rapidly disintegrating. In other words, it would need to resemble a small planetary core more than a fluffy cometary nucleus. Grounded estimates help to focus this tension. Suppose, in round numbers, that maintaining the third tail requires the loss of several tons of dust and gas each second, superimposed on the already substantial flow that feeds the traditional tails. Over the course of a day, that becomes hundreds of thousands of tons. Over weeks, the total climbs into figures that begin to rival a significant fraction of a modest mountain. If 3-eye Atlas were a typical, low-density comet, honeycombed with pores and fractures, this level of sustained erosion should leave visible scars. The nucleus should fragment, spin up, or show other signs of stress. Yet the available data, limited though they are, do not obviously display that kind of catastrophic unraveling. There are ways to soften this apparent contradiction without abandoning natural explanations. One is to suggest that our eyes are being fooled about the density of the sunward feature. The third tail may look solid, but in reality could be a very sparse collection of grains, arranged and lit in a way that exaggerates their cohesion. A relatively modest mass loss could then produce a surprisingly bright line, especially if the grains are of a size and composition that scatter sunlight efficiently. Another possibility is that only a fraction of the apparent length of the channel is truly filled with fresh material at any given moment. The rest might be a fading echo, a record of earlier ejecta that no longer demands energy to maintain. Yet even these more conservative pictures keep circling back to the same quiet query. Why does 3-eye Atlas seem able to route material into a coherent, sunward-oriented lane when most comets, under similar solar conditions, cannot? If the nucleus is compact and dense, perhaps because it is the stripped core of a much larger body, then its gravity and internal structure might support stronger and more localized outflows. If its surface hides regions of stronger cohesion, like exposed bedrock on a world that has lost its softer mantle, then vents could focus material into jets that feel more like pressurized fountains than gentle leaks. In such a scenario, the energy budget is still tight, but the underlying engine is more robust than that of a fragile snowball. For listeners drifting towards sleep, the numbers themselves may blur, but the shape of the argument can remain. Imagine keeping a narrow beam of water flowing from a hose against a stiff wind. The harder the wind blows, the more pressure you need at the source to keep the stream from curling away. Solar radiation and the solar wind play the role of that invisible gust, pushing relentlessly outward. If 3i Atlas is managing to maintain a sunward directed channel in such an environment, it is like a hose that refuses to be bent, implying either unusually high pressure at the nozzle or some guiding structure that shields and directs the stream. The energy budget problem does not, by itself, demand exotic answers. It does, however, gently steer our attention toward models where 3i Atlas is more than a loose assembly of volatile ices. It encourages us to consider a nucleus that is denser, more structured, perhaps layered, with regions capable of sustaining focused outflows without tearing themselves apart. That is one of the reasons planetary core hypotheses begin to sound less like wild speculation and more like reasonable options on the table. A compact remnant of a broken dwarf planet would bring with it both the mass and the internal strength needed to support long-lived, organized features. As our journey continues, the question will sharpen. If a standard comet struggles to balance the books required for a stable third tail, what kind of interior composition makes the ledger close more neatly? Is 3i Atlas simply an extreme case at the edge of known comet behavior, or is it quietly advertising a different category of object, one in which the line between comet and planetary fossil blurs? In the next part, we will look not only at how much energy is spent, but at how that energy might be organized, turning from raw budgets to the subtler choreography of rotation, vents, and spin, and asking how a body that turns once every 16 hours can still produce structures that seem to stand almost perfectly still. If you imagine holding a small, irregular stone in your hand and slowly turning it over, you have a fair picture of what astronomers think most comet nuclei are doing as they travel through the inner solar system. They spin, sometimes quickly, sometimes lazily, about axes that are tilted at odd angles. Sunlight falls unevenly across their surfaces, heating some regions while others lie in shadow. Wherever the warmth is strong enough, gases escape, carrying dust with them in jets that fan out into space. Over time, as the body continues to spin, those jets trace graceful spirals and broad plumes, the natural signature of a rotating, outgassing world. When the rotation period is known, there is an expectation that certain patterns should follow. For 3i Atlas, the best current analyses suggest a rotation period on the order of 16 hours. In practical terms, that means that during a single Earth night, the interstellar visitor can turn almost a full revolution. Any vents fixed on its surface, especially those near the equator of its spin, should therefore present different faces to the sun over the course of an observing run. A jet that points sunward at the beginning of the night should swing to the side and then away as the hours pass. Long exposures taken under these conditions usually show this motion in subtle ways. Tails appear slightly curved, jets look like gently swept fans rather than narrow beams, and repeated images taken over several nights reveal evolving patterns that track the spin. The paradox in the case of 3i Atlas is that the third structure in the Rayong images behaves as if this rotation barely matters. Instead of displaying the soft, swept appearance of a plume attached to a spinning surface, the sunward channel looks rigid and straight, almost indifferent to the 16-hour cycle. Observers who composite frames taken at different times during a night do not report the kind of smeared spiral one would expect from a simple equatorial jet. Instead, the feature maintains a consistent alignment toward the sun, as if anchored not to a spinning rock, but to some larger structure that does not share the nucleus's restless turning. The main dust tail and the ion tail can still show the gentle curvature and shifting emphasis typical of a rotating source, but the third channel cuts through these variations like a fixed line. There are, as always, conservative ways to approach this. One is to consider the possibility that the active source feeding the sunward feature lies close to a rotational pole. If the spin axis of 3I Atlas happens, by chance, to point roughly toward the sun, then a vent near that pole would maintain a nearly constant orientation relative to the incoming radiation. In that geometry, the 16-hour rotation could proceed without dramatically altering the direction of the jet, and the third tail could appear straight in images even though the nucleus beneath it is spinning. This idea does not require new physics. It asks only for a particular alignment, the kind that sometimes occurs in the varied family of comets we have already studied. Yet when this picture is pushed a little further, questions arise. A polar vent can explain a stable direction, but it does not fully account for the concentrated, beam-like character of the sunward structure. In many comets where polar activity is suspected, the resulting plumes are still broadened by the combined effects of rotation, local turbulence, and interaction with the solar wind. They may hold a general orientation, but they rarely collapse into a narrow, persistent channel that seems to sharpen over time. In addition, a spin axis that points close to the sun would leave fingerprints in the way the nucleus brightens and fades as it moves along its path. Light curves, those careful measurements of brightness over time, can sometimes distinguish between equatorial and polar activity. For 3I Atlas, the emerging light curve does point to a roughly 16-hour period, but it does not immediately settle the question of whether the activity is concentrated near the poles or spread more widely, leaving some ambiguity in the polar vent scenario. Another avenue of grounded speculation focuses on the timescales baked into the images themselves. Even if 3I Atlas spins once every 16 hours, each individual exposure from Rayong may last only a few minutes, and the total span of a nightly observing run might cover a fraction of a full rotation. Perhaps then, the apparent rigidity of the third tail is partly an illusion born of sampling. We might be catching the object at similar rotational phases on different nights, or stacking frames in a way that emphasizes the most stable parts of the structure while allowing smaller variations to wash out. If that were the whole story, however, we would still expect at least some hint of curvature or fan, like spreading in the deepest composites, especially when data from multiple nights are combined. The stubborn straightness of the third channel keeps that explanation from feeling completely satisfying. At this point, the spin paradox begins to guide us toward models where rotation and outflow are not the only actors on the stage. In addition to gravity and sunlight, comets move through a medium of charged particles and magnetic fields. Dust grains can become electrically charged as they leave the surface, and gas can be ionized, turning parts of the coma and tail into a kind of flowing plasma. If 3I Atlas has an internal structure rich in metals or other conductive materials, its rotation through the solar wind could induce magnetic effects, however modest, that interact with this plasma. In that picture, the third tail may not simply be a jet painted across space by the spinning nucleus, but a stream of charged particles that quickly couples to a local magnetic field configuration, one that remains relatively fixed even as the underlying body turns. This idea sits at the boundary between familiar comet science and the more specialized domain of dusty plasma physics. It does not require strong, planet-sized magnetic fields. Even weak fields, combined with the right distribution of charged grains, can encourage material to follow preferred paths. If those paths happen to align roughly with the line to the Sun, then a rotation period of 16 hours becomes less important. The particles, once launched, would be guided by field lines rather than by the changing orientation of their source. The sunward channel would then be a kind of magnetic conduit, appearing straight and stable in images, not because the nucleus is stationary, but because the shaping forces operate on scales larger than the body itself. For a listener lying in the dark, this may sound abstract, but you can translate it into a simpler picture. Think of a rotating lawn sprinkler that is spraying water into a steady breeze. If nothing else is present, the streams trace arcs and fans, clearly revealing the spin. Now imagine that thin, invisible rails are placed in the air, and as soon as the droplets leave the nozzle, they are drawn onto those rails and guided in straight lines. The sprinkler continues to turn, but the pattern seen from a distance is dominated by the rails, not by the rotation. In a similar way, if magnetic structures around 3I Atlas are strong enough to organize the flow of charged particles, the usual rotational signatures could be suppressed, leaving behind the kind of rigid, sunward feature that the Rayong images suggest. The beauty of approaching the spin paradox in this grounded way is that it invites testable questions. If the third tail is truly tied to magnetic or plasma effects, rather than to simple vent geometry, then its response to changes in the solar wind should differ from that of the main dust and ion tails. Subtle shifts in orientation or brightness correlated with solar activity might reveal whether we are seeing a vent locked into a fortunate polar alignment or a more elaborate interaction between rotation, charge, and field. Later, when we talk about how an incoming coronal mass ejection may act as a natural experiment on 3I Atlas, this distinction will become even more important. For now, the puzzle remains gently unresolved. A 16-hour rotation period promises a certain choreography of jets and plumes, yet the sunward structure observed from Rayong appears to stand almost outside that dance. Whether the explanation lies in a lucky polar vent, in the invisible architecture of magnetic fields, or in some combination of the two, the spin paradox serves as another quiet reminder that 3I Atlas is not easily folded into the standard comet template. As you let your mind drift, you might hold that image of a rotating stone in space, wrapped not in smooth, symmetrical streams, but in one particularly stubborn, straight channel of light, and ask what hidden structure inside or around this interstellar visitor makes such defiance of simple rotation possible. By now, the third tail of 3I Atlas has asked questions about geometry, about the cost of maintaining a narrow channel, and about how a spinning body can produce something that looks almost independent of its rotation. There is one more quiet actor we have not yet given center stage. It is the simplest and most pervasive influence in this story, the thing that makes comets beautiful in the first place. It is sunlight itself, not just as illumination, but as a steady, physical push. To understand why a sunward pointing structure is so unsettling, we need to sit for a moment with the idea that every beam of light is also a wind, and that the tails we see are, in a very real sense, carved by that invisible pressure. In an everyday life, light seems gentle. It warms your skin, brightens a room, glints off glass and water, but it does not feel like it is pushing you. In the vacuum around the sun, where there is nothing to cushion the effect, the story is different. Photons carry momentum. When they strike a dust grain and are absorbed or reflected, they transfer a tiny shove. For a grain that is small and light, that shove is not trivial. Over hours and days, countless shoves add up, nudging the particle away from the sun. At the same time, a stream of charged particles flows outward from the star as the solar wind, sweeping ions into long, straight tails. Together, radiation pressure and the solar wind act like a constant gale, ensuring that most of the visible material around a comet is eventually encouraged to move outward, roughly along the line away from the sun. That is why, in almost every textbook illustration, tails point anti-sunward, trailing behind the comet's motion like smoke in a steady breeze. Against that backdrop, the Rayong images of 3I Atlas seem almost perverse. The main dust tail behaves as expected, curving away from the sun in a soft arc. The ion tail follows the direction of the solar wind, straighter and narrower, but the third feature, the one that has drawn so much attention, leans in the opposite direction, aligned toward the sun instead of away. It is as if, in the middle of a windstorm, you saw a plume of smoke pouring steadily into the gust rather than being carried downstream. For that to happen without breaking any laws, the smoke would need to be very heavy, or it would need to be held in place by something stronger than the wind. The same logic applies here. Either the grains in the sunward channel are unusually massive, so that radiation pressure is too weak to turn them, or some other force is quietly overruling the outward push. The heavy grain picture is, at first, appealing. Larger particles, perhaps grains a millimeter or more across, feel the sun's gravity more strongly relative to radiation pressure than tiny specks do. When they leave the surface of 3I Atlas, they do not get blown into long, wispy tails as easily. Instead, they follow paths closer to the natural orbit of the nucleus, lagging and bunching in ways that can, under certain viewing angles, create the impression of a sunward structure. Models of comet dust often show that mixtures of sizes can produce complex patterns, with fine grains making broad, bright tails and heavier grains contributing to subtler, more localized features. If the third tail is dominated by such heavier material, then its resistance to being swept outward becomes less mysterious. But heavy grains bring their own complications. Because they are fewer in number and scatter light less efficiently per unit mass than fine dust, they usually produce dimmer, more diffuse structures. The Rayong channel, by contrast, appears relatively sharp and conspicuous. To make it so visible, using mainly large particles would require a significant mass flow, pushing us back toward the energy budget concerns we explored earlier. There is also the question of coherence. Even massive grains, once released, move under a combination of solar gravity and the weak but persistent push of radiation pressure. Over time, their trajectories diverge. Without some organizing influence, a narrow stream of heavy particles should slowly fan out, softening its edges. The images of 3I Atlas suggest a feature that remains better defined than that simple picture would predict. Another way to think about the problem is to imagine the interplay between orbital motion and radiation pressure over weeks. Detailed models, sometimes called syndine and synchrone calculations, trace how dust released at different times and with different sizes spreads along curves determined by these forces. For many comets, those curves can account for subtle spikes and lanes in the tail, including occasional anti-tail like structures when Earth's viewpoint and the dust distribution align. In those models, however, the sun is always winning in the long run. Small grains are swept away quickly, and even larger ones slowly drift outward. A long-lived, sunward-aligned channel that seems to tighten rather than diffuse suggests that something is shaping the dust more directly than the usual combination of gravity and photon pressure alone. That is where the idea of another force enters, not as an exotic intrusion, but as a reminder that space near the sun is not empty. It is threaded by magnetic fields carried outward by the solar wind, forming a vast, spiraling structure, sometimes compared to a garden sprinkler frozen in slow motion. When gas is ionized and dust grains acquire electric charges, they begin to feel not just the push of light and the pull of gravity, but also the tug of these fields. Their motion can then be constrained along invisible pathways, much as iron filings arrange themselves along the lines of a bar magnet on a tabletop. In most comets, these effects contribute to the appearance of the ion tail, giving it its straight, filamentary look. In the case of 3I Atlas, the possibility arises that charged dust is being woven into a similar but more unusual pattern, one that happens to align roughly toward the sun. For that to happen in a sustained way, some local structure would help. If 3I Atlas has an internal composition that allows currents to flow, even weakly, then its motion through the solar wind could create a kind of miniature magnetosphere. The fields associated with that magnetosphere would interact with the larger scale interplanetary field, creating regions where charged grains are trapped or guided. In this grounded speculation, the third tail is less a boas plume and more a corridor carved by those interactions, a place where particles that would otherwise be blown away are instead held in a relatively tight formation. The apparent defiance of radiation pressure is then not a true reversal, but a redirection. The grains still feel the push of light, but their paths are bent along field lines that happen, from our viewpoint, to trace a line back toward the sun. If you prefer a more intuitive picture, you might think of a river flowing downhill while narrow channels and eddies guide part of the flow upstream along the bank. The overall motion is still downward. Gravity has not changed. But local features in the landscape can temporarily reverse the visible direction of the water. In space, radiation pressure and the solar wind provide the overall push away from the sun. The magnetic and electric environment near 3I Atlas may provide the channels and eddies. To an observer on Earth, the net result could be a stream of material that seems to reach sunward, not because the basic rules are broken, but because they are being applied in a landscape more complex than the simple diagrams on a classroom board. This line of thinking connects naturally to the idea of 3I Atlas as something denser and more structured than a typical comet. A nucleus with a metallic or partially differentiated interior would be better suited to hosting the currents and magnetic effects needed to shape a dusty plasma into narrow lanes. It does not force us to adopt a planetary core hypothesis, but it certainly makes such a hypothesis feel more compatible with the observed behavior. It is easier to imagine a compact, relic fragment of a long destroyed world sustaining an intricate interaction with the solar wind than a fragile snowball doing the same. The triple tail structure then becomes not just a curiosity, but a possible signature of that deeper character. For scientists who model these systems, the challenge now is to weave radiation pressure, gravity, and electromagnetic forces into a single, coherent picture that can reproduce what Rayong and other observers have seen. Can a mixture of grain sizes, realistic charging, and plausible field geometries create a sunward channel that remains sharp as the weeks pass? Or does the persistence and alignment of the third tail push us toward acknowledging that our current treatment of dust dynamics around the interstellar visitors, like 3I Atlas, is incomplete? These questions are not accusations against the existing physics, but invitations to refine and extend it. As you rest and let the scene settle in your mind, you might return to that simple, quiet puzzle. Light, which should always push dust away, seems to coexist here with a feature that points back toward its source. Is that feature a cleverly arranged stream of heavy grains, a magnetic corridor sculpted by a compact, unusual nucleus, or some combination of both? In the next part of this journey, we will turn more directly to the nature of that nucleus itself, asking what kind of object can sustain such intricate interactions with sunlight and plasma, and whether 3I Atlas is best understood as just another comet or as the exposed, traveling core of a much larger story written in the deep past of some distant planetary system. We have circled around the strange geometry and the delicate balance of forces shaping the triple tail of 3I Atlas, and each loop has quietly pointed back to the same simple question: what kind of body can afford to behave this way? At some point, the puzzle of the tails becomes a puzzle of the interior. If a loose, low-density snowball struggles to explain a stable, sunward channel and a generous mass loss budget, then perhaps 3I Atlas is not a snowball at all. Perhaps it is closer to a stone heart, the compact remnant of something that was once larger and more complicated, stripped of its outer layers and left to wander between the stars as a planetary fossil disguised as a comet. To see why that idea carries weight, it helps to contrast the textbook comet with a small world that has gone through a deeper history. A typical comet nucleus is imagined as a porous mix of ices and dust, fragile, riddled with cavities, a kind of frozen sponge that falls apart if stressed too hard. Its average density is often less than that of water. A planetary core, even a modest one, lives at the opposite end of that spectrum. In the early days of a planetary system, heat and radioactivity can cause heavier elements to sink inward and lighter materials to float outward, a process called differentiation. The result is a layered structure with a central ball of rock or metal wrapped in a mantle and, in some cases, an icy shell. If such a world is later shattered by collisions, fragments of its interior can be thrown outward, compact, dense, and far more resistant to erosion than a simple snowball. Our own solar system offers hints that such fossils exist. Some asteroids appear to be almost pure metal, likely the exposed cores of once larger bodies that lost their mantles in violent impacts. Others show signs of having once been warm enough to differentiate, even if they are now cold and inert. The Oort cloud that surrounds our system is usually described as a reservoir of icy comets, but it may also harbor fragments of partially differentiated worlds, small cores, and thick crusts that were exiled to the outskirts during the chaotic rearrangements of the giant planets. If that has happened here, it is reasonable to imagine that other planetary systems have experienced similar violence, populating interstellar space with compact remnants that only occasionally wander close enough to another star to be seen. When the first known interstellar visitor, often called One-Eye Oumuamua, swept through the inner solar system, its odd shape and non-gravitational acceleration sparked intense debate about its nature. The second, Two-Eye Borisov, looked more like a conventional comet, with a familiar coma and tail. In that small sample, we already see a hint of diversity. Three-Eye Atlas, if it truly exists with the properties suggested by current reports, may extend that diversity further, occupying a middle ground between comet and compact remnant. It does not need to be an engineered object to be unusual. It can simply be a shard from the deep interior of a long vanished world, carrying that world's density, magnetic tendencies, and stubborn resistance to crumbling into dust. A body like that would bring several advantages to the problem we face. A dense, cohesive nucleus can sustain higher outgassing rates without tearing itself apart. Vents can excavate dust and gas from specific regions without immediately destabilizing the whole structure. Gravity at the surface, while still weak by everyday standards, is stronger than on a fluffy aggregate, helping to shape the initial flow of particles. If the interior contains metals or other conductive materials, rotation through the solar wind could induce weak but meaningful magnetic fields, providing the scaffolding on which dusty plasma can organize itself into channels and filaments. The triple tail of Three-Eye Atlas would then be less a surprising extravagance and more a natural consequence of a compact, structured engine sitting at the center. Thermal behavior also changes when you move from a sponge-like nucleus to a planetary fossil. Low-density comets respond quickly to sunlight, with surface layers heating and cooling over short timescales. Dense bodies have higher thermal inertia. Heat penetrates more slowly, and in internal reservoirs can continue feeding activity even when the immediate surface cools. That can support long-lived jets and maintain complex structures in the coma over many rotations. In a planetary core scenario, the vents feeding the third tail of Three-Eye Atlas might tap into deeper layers where volatiles are stored in fractures or pockets, releasing material in a more controlled, sustained way than a simple surface frost would allow. From an observational standpoint, there are subtle markers that can hint at such an interior. The way brightness changes with distance from the sun, the specific mix of gases seen in spectra, and the presence or absence of certain dust signatures all feed into models of density and composition. A planetary fossil might show a relatively muted response in overall brightness, but host localized high-contrast features in its tails, a kind of quiet nucleus surrounded by surprisingly disciplined structures. It might also display a rotation state that is unusually stable, suggesting a strong internal coupling rather than the loose tumbling sometimes seen in smaller, more fragile bodies. None of these clues, taken alone, prove that Three-Eye Atlas is a planetary core. Together, however, they sketch a picture that fits more comfortably than the standard idea of a loosely bound comet. The mass loss implied by the energy budget, the stubborn stability of the third tail, the hints of organized dusty plasma behavior all lean toward a nucleus that is denser and more structured than average. In that sense, the planetary fossil hypothesis is not a leap into fantasy, but a grounded attempt to match interior properties to exterior behavior. It allows us to explain a complex, triple-tailed morphology without invoking new forces or technology, only by recognizing that not all small bodies share the same deep history. For a listener lying in the dark, this can be a strangely calming thought. Somewhere out there, 3i Atlas may be carrying the compressed story of a broken world, a world that formed, differentiated, perhaps hosted a brief period of warmth and chemistry, and was then torn apart and exiled into interstellar night. The object we see now is just its remaining heart, warmed once more as it passes near our sun, briefly revealing its structure in the language of tales and plasma. When we speak of a planetary fossil, we are not romanticizing at the expense of rigor. We are acknowledging that the shapes we see in a comet's wake may be the last, delicate handwriting of planets that no longer exist. The open question, the one that lingers even after the models are run, is where that lost world once orbited. Did 3i Atlas begin its life in a system like our own, with rocky inner planets and distant giants, or did it belong to a place with a very different architecture? Are we watching the remnant of a dwarf planet that never quite grew up, or of a larger body that met a violent end? In the next stage of this journey, we will look more closely at the plasma physics that might allow such a compact nucleus to sculpt its environment into magnetic cages and self-organizing channels, and ask how far we can go in explaining the triple tail of 3i Atlas before we have to admit that its behavior, while grounded in known forces, still feels just beyond the edge of our current intuition. By now, the space around 3i Atlas may feel almost crowded in your imagination. We have sketched sunlight pushing on dust, solar wind streams, and the quiet gravity of a dense, possibly fossilized nucleus. To complete this picture, we have to let one more layer settle over it all, a layer that does not show up directly in images, but reveals itself through patterns and filaments. That layer is dusty plasma, a state of matter where gas, ions, electrons, and tiny solid grains share the same volume and interact in ways that are both subtle and surprisingly organized. Comet Comets are natural laboratories for dusty plasma. When sunlight ionizes gas streaming from the surface, free electrons and ions mix with neutral molecules and dust. The dust grains can absorb or lose electrons, becoming charged. Suddenly, those grains are no longer governed only by gravity and radiation pressure. They begin to feel the presence of electric fields and magnetic fields, and the empty space around a comet turns into a medium where forces can sculpt structure in 3 dimensions. In familiar comets, this dusty plasma environment is responsible for some of the most delicate features we see. Ion tails often break into strands and rays, tracing regions where magnetic field lines have gathered charged particles into filaments. Disconnection events, where a portion of the tail seems to detach and drift away, can occur when a changing solar wind field snaps or reconfigures those lines. None of this violates the basic rules of physics that we teach in classrooms. It is simply the behavior of charged matter in a magnetic environment. Yet even within that framework, the efficiency with which fields can collect and hold material can be surprising. A very small change in the local magnetic field can redirect the flow of gas and dust on scales of thousands of kilometers, turning what might have been a blurred cloud into an intricate pattern of bands and streaks. If we bring that understanding back to 3-Eye Atlas, the idea of a magnetic cage begins to feel less like a metaphor and more like a practical description. Imagine the nucleus as a compact object with regions of conductive material buried beneath its surface. As it moves through the solar wind, it cuts through the large-scale magnetic field that spirals outward from the sun. That motion can induce currents, and those currents can generate a modest magnetic field of the object's own. The result need not be dramatic. Even a weak, localized magnetosphere could change the way charged particles move near the nucleus. Ionized gas and charged dust grains might become trapped along closed loops of field or guided along open lines that connect to the broader interplanetary field. In such a landscape, the triple tail of 3-Eye Atlas would not simply be a set of passive plumes, but a visible map of where those invisible lines have collected matter most effectively. The phrase magnetic cage suggests confinement, and that is exactly what these structures can provide. When charged grains enter a region where field lines converge or form a bottle-like configuration, their motion perpendicular to the lines is restricted. They spiral around the lines, bouncing back and forth between regions of higher field strength. While they still drift slowly, their paths are no longer free. In the case of 3-Eye Atlas, one can picture a configuration in which a set of field lines happen to form a narrow corridor that points approximately toward the sun. Charged dust entering this corridor would be more likely to stay within it, building up a higher density of material than in surrounding regions. From Earth, that corridor would appear as a narrow, sunward tail, a tangible signature of an otherwise invisible scaffold of magnetism. There are a few hard facts that make this picture more than pure imagination. Spacecraft that have flown through Comet Coma, such as missions to Comet Halley and Comet 67P Churyumov-Gerasimenko, have measured electric and magnetic fields that vary sharply over small distances. They have observed regions where dust and plasma act together, sometimes forming boundaries and cavities reminiscent of miniature magnetospheres. In some cases, the local environment around a comet has even been described as a kind of dusty plasma bubble where the coupling between gas, dust, and fields creates zones that are partially shielded from the surrounding solar wind. If such complexity can arise around small, relatively ordinary comets, it is not unreasonable to suspect that a dense, magnetically interesting object like a planetary fossil could produce even more dramatic effects. Grounded speculation then suggests a layered structure around 3-Eye Atlas. Closest to the surface, vents release gas and dust, setting the raw material into motion. Slightly farther out, ultraviolet light and collisions strip electrons from molecules, creating ions and charging dust grains. Beyond that, on scales of tens of thousands of kilometers, the interaction between this charged mixture and the magnetic field shapes the flow into preferred channels. Two of those channels align in more familiar directions, giving rise to the main dust and ion tails. A third, more unusual configuration happens to focus material along a field structure that, from our vantage point, is oriented sunward. The result is the triple tail pattern that has become the focus of so much attention. There is an elegance to this explanation. It does not ask for a break in the known laws, only for an object with the right internal properties to generate a rich external environment. A denser, partially metallic nucleus fits naturally into that role. The planetary fossil picture and the dusty plasma picture reinforce each other rather than compete. A compact core is the engine. The dusty plasma is the medium. The magnetic cage is the mechanism that turns energy and mass into precise, persistent structures. From this perspective, 3i Atlas becomes less of a rule breaker and more of a special case that pushes known physics into a new corner of its parameter space. At the same time, this model carries a humbling reminder. Our intuition about how dust and gas should behave around small bodies has been shaped by a limited sample. Most of our detailed measurements come from a handful of comets in our own solar system. An interstellar visitor, like 3i Atlas, may bring compositions and internal architectures that we have not yet fully anticipated. The triple tail may be a preview of how diverse dusty plasma structures can become when different kinds of nuclei are exposed to the same solar wind. In that sense, every unusual filament and channel in the images is a quiet data point in a much larger experiment, one that spans many planetary systems and billions of years of history. As you lie back and picture this in the dark, you might imagine 3i Atlas not just as a solid body moving through space, but as the center of a faint, living aura of charged dust and gas. Within that aura, unseen lines loop and twist, guiding particles into streams that our telescopes translate into light. The third tail is one of those streams, made visible because the concentration of material along its path is just high enough to catch our attention. Is this magnetic cage model the final word, or only a step toward a more complete description? That question remains open, and it is part of what makes watching this object so absorbing. In the chapters ahead, we will see how this delicate architecture of dusty plasma may respond when the quiet, steady solar wind is replaced by a more violent visitor of its own, a coronal mass ejection racing outward from the sun. Will the magnetic cages around 3i Atlas bend and flex, preserving the triple tail, or will they be torn open, releasing their carefully guided streams into a more chaotic pattern? The answer will tell us not only about one interstellar object, but about how resilient such plasma structures can be when the calm background turns into a storm. In the story of 3i Atlas so far, each layer of explanation has added structure to what began as a simple, striking picture from Rayong. Geometry suggested that our point of view might be involved. Energy budgets hinted at an object that could afford sustained, focused activity. Dusty plasma and magnetic cages offered a way for fields to channel material into narrow lanes. There is one more concept that can quietly link these pieces together. It is the idea that under the right conditions, systems like this can begin to organize themselves, turning random motion into patterns that persist without any need for an external designer. Self-organization is a familiar theme in nature once you start noticing it. Grains of sand on a beach can line up in ripples under the action of waves. Clouds can form bands and streets under steady winds. In the laboratory, dusty plasmas placed in microgravity have been observed to form crystalline arrangements, with charged particles settling into delicate, lattice-like structures, because that is the configuration that balances their mutual repulsion and the forces confining them. No one places each grain by hand. The pattern emerges because the system explores many possibilities and quietly prefers the ones that are stable. Around 3i Atlas, the ingredients for a similar process are all present. Dust grains leave the surface with a range of sizes and speeds. Ultraviolet light strips electrons from some of them. Collisions and charge exchange processes redistribute those electrons, leaving grains with differing charges. Magnetic fields, whether induced by the motion of a conductive nucleus or carried in by the solar wind, thread through this charged mixture. Gravity from the nucleus, weak but persistent, tugs inward. Radiation pressure continues to push outward. Each grain feels a slightly different combination of these influences, and over time, the chaotic swarm of trajectories begins to favor certain paths over others. Regions where forces balance in a relatively stable way become preferred routes. In such an environment, narrow channels can form almost as a side effect. If there is a corridor where the magnetic and electric forces guide charged grains along a particular set of field lines, new grains entering that region will tend to follow those paths. Once a filament develops, its presence can subtly influence the fields and flows around it, encouraging further concentration. The result is a kind of feedback loop. A tenuous lane forms, draws in more material, and becomes more distinct. At the same time, areas where motion is more chaotic may empty out, leaving gaps that make the lanes stand out more sharply. From a distance, what you see is not an imposed structure, but an emergent one, a self-maintaining pattern that remains as long as the underlying conditions persist. This perspective offers a way to think about the triple tail of 3I Atlas that is both grounded and quietly elegant. The main dust and ion tails occupy the more familiar regions of parameter space, where radiation pressure and the bulk flow of the solar wind dominate. The third, sunward channel, may represent a self-organized filament in a dusty plasma, a place where charged grains have discovered, through their collective motion, a path of least resistance that happens to align roughly with the line back to the sun. Once established, that filament would not need constant fine-tuning. As long as the supply of grain continues and the magnetic environment does not undergo a drastic change, the structure can renew itself, explaining its persistence and apparent sharpening over multiple nights. There are hints in existing comet observations that such processes are already at work on smaller scales. High-resolution images of jets and inner Comets show braids, rays, and sharp boundaries that are difficult to explain with simple, one-dimensional outflow models. Spacecraft flybys have recorded sudden changes in local plasma properties over distances of only a few kilometers, as if crossing invisible strands. In laboratory dusty plasmas, researchers watch as filaments appear, fade, and reconnect under small changes in driving conditions. Each of these examples is a reminder that when charged particles and dust share the same space, complexity is the rule rather than the exception. The difference with 3I Atlas may be that one of these self-organized features has grown large and stable enough to be seen clearly from millions of kilometers away. If this is the case, then the triple tail structure becomes not just a curiosity of one interstellar object, but a window into a regime of physics that we have only glimpsed in fragments. It would suggest that planetary fossils and other dense nuclei moving through stellar winds can act as seeds for grand-scale, dusty plasma sculptures, patterns that encode the interplay between interior composition and external environment. It would also mean that our first instinct, to treat the third tail as a simple anti-tail or a single jet, may underestimate how much collective behavior is hidden in that thin line of light. What looks like a single stroke may, in reality, be the combined handwriting of countless grains, each following its own equation of motion, all together producing a coherent signature. For a listener resting under a dark ceiling, this idea of self organization can be strangely reassuring. It says that the universe is capable of building intricate, delicate arrangements without needing to plan them in advance. It says that order can arise from the quiet negotiation of many small influences, even in a place as apparently empty as the space around 3i Atlas. You might picture the triple tail not as a rigid beam, but as a constantly renewed procession, grains entering, traveling, and leaving, so smoothly that the pattern looks almost frozen from our distant vantage point. As this part of the journey closes, the hypotheses we have gathered form a kind of layered map. At the surface, 3i Atlas may look like an unusual comet. Beneath that, it may be a dense planetary remnant capable of sustaining stronger, more focused activity. Around it, dusty plasma and magnetic fields may weave cages and channels, allowing charged grains to self-organize into persistent filaments. Each step remains within the boundaries of known physics, yet together they produce a structure that feels new. In the next stage, our attention will turn outward again, away from the internal engine and its immediate halo to the larger environment of the solar wind. There, a different kind of structure is racing outward from the sun, a coronal mass ejection whose impact on 3i Atlas will act as a natural experiment, testing whether the self-organized triple tail can survive a storm or whether it will be torn apart and rewritten before our eyes. By the time the triple tail of 3i Atlas had settled into something almost familiar in the minds of the people watching it, another structure had already begun to form much closer to home. On the surface of the sun, magnetic fields twisted and knotted until, over the course of a few tense hours, they snapped and rearranged, flinging a great bubble of plasma out into space. From our distance, this event does not look like a flare of fire leaping from the solar disk. It appears instead as a pale, expanding halo in coronagraph images, a faint ring swelling outward as though someone had breathed gently into the fabric of the solar wind. That halo is a coronal mass ejection, a moving cloud of charged particles and tangled magnetic fields, and in the quiet calculations of space weather centers, its path begins to be traced. Unlike the steady background wind that constantly streams from the sun, a coronal mass ejection is a surge, a sudden thickening and speeding up of the flow. It can carry billions of tons of solar material spread across a vast front, traveling at hundreds of kilometers per second. When such a structure crosses Earth's orbit, it can compress our planetary magnetic field, spark auroras, and disturb satellites. When it passes farther out, through the region where 3i Atlas is now moving, it becomes something different. It is no longer just a potential source of geomagnetic storms. It is an experiment the sun has launched, an involuntary stress test that will sweep across the delicate plasma environment we have been trying to imagine around this interstellar visitor. At first, the connection between the eruption on the sun and the small point of light that is 3i Atlas exists only in numbers. Space weather agencies release estimates of speed and direction. Astronomers compare those with the predicted position of 3i Atlas days or weeks in the future. Lines are drawn on charts. Uncertainties are acknowledged. Slowly, a picture forms. The expanding front of the coronal mass ejection and the projected path of 3i Atlas appear to intersect. The timing, when converted from models and tables into simple dates, suggests that around the 22nd of November, the cloud will sweep across the region of space the object occupies. It is not a precise appointment, the way a spacecraft flyby would be. It is more like knowing that a storm front and a drifting boat will likely share the same patch of ocean sometime during a given night. For observers on the ground, this realization changes the rhythm of watching. Until now, the triple tail has been a slowly evolving puzzle. Images from Rayong and other sites showed its sunward channel sharpening, its stability hinting at magnetic cages and self-organizing dusty plasma. There was time to linger over each frame, to refine models, to argue gently about planetary fossils and the limits of standard comet physics. With a coronal mass ejection on the way, that spacious feeling narrows. The sun has, without any regard for our schedules, put a countdown clock on the current configuration of 3I Atlas. Whatever the triple tail is made of, and however it is being held together, it is about to be pushed, squeezed, and briefly drowned in a denser, more chaotic flow. To understand what that means, it helps to imagine the difference between standing beside a slow, steady river and standing on the bank when a sudden flood wave arrives. The background solar wind is the river, always there, shaping the tails in a relatively predictable way. A coronal mass ejection is the surge, carrying with it not just more particles, but stronger and rapidly changing magnetic fields. As the front of the ejection sweeps over 3I Atlas, the pressure on its plasma environment will rise. Field lines that were gently guiding charged grains may be bent or compressed. Regions that acted as magnetic cages may be shaken, their carefully balanced configurations disturbed. In that brief interval, the triple tail does not exist in the same calm context that allowed it to form. It exists inside a moving laboratory where the knobs on pressure and field strength have been turned up without warning. From the perspective of Earth, nothing dramatic happens in real time to signal this collision. There is no visible flash on the sky when the front of the coronal mass ejection reaches 3I Atlas. Instead, the changes show up in the slow accumulation of images. Astronomers plan a series of observations spaced across the expected arrival window. Some stay with modest telescopes in small observatories. Others petition for time on larger instruments that can probe the structure of the tails more deeply. Each exposure taken before the storm becomes a baseline. Each exposure during and after becomes part of a natural before and after experiment that no human agency could have arranged so economically. The questions they hope to answer are simple to state. Does the main dust tail of 3 Atlas kink, twist, or shed material in a way consistent with a sudden change in solar wind conditions? Does the ion tail show signs of disconnection, as has been seen in other comets when strong solar disturbances pass by? And, most pointedly, what happens to the third, sunward channel? Does it blur, break, or vanish along with any disturbed plasma structures, or does it reappear quickly, perhaps even unchanged, once the front of the coronal mass ejection has passed? Each of those possibilities points toward a different balance of forces at work. If the triple tail proves fragile, dissolving under the increased pressure and field turbulence of the storm, then the case for subtle, finely tuned magnetic cages becomes stronger. It would suggest that the structure we have been watching is a delicately poised arrangement, impressive but easily disrupted when conditions shift too abruptly. The sun's outburst would then serve as a reminder that even the most striking self-organized patterns in dusty plasma are temporary, dependent on a background that remains within certain bounds. If, on the other hand, the sunward channel survives with only minor distortions or reforms quickly in the same orientation, then a different conclusion begins to take shape. That outcome would hint at underlying anchors, perhaps in the form of a strong, persistent magnetic framework tied to the dense nucleus of 3I Atlas that can reassert its influence even after being briefly overwhelmed. For those listening as they drift toward sleep, the idea of this impending encounter can be held as a kind of quiet suspense, not the sharp anxiety of a disaster movie, but the softer anticipation of an experiment whose results will be interesting no matter how they turn out. There is no danger to Earth in this scenario, no looming impact, only the distant meeting of a moving cloud and a small, complicated object. What is at stake is not safety, but understanding. We are watching to see whether the story we have begun to tell about planetary fossils, dusty plasma, and magnetic cages is resilient, or whether the sun will, with one passing gesture, show us that our narrative needs further refinement. In the next part of this journey, we will step back from 3I Atlas for a moment and look at other times when comets have been caught in similar storms. By revisiting those disconnection events, where tails were quite literally torn away by passing disturbances, we can build a scale for what is normal. Then, when fresh images of 3I Atlas arrive from the days around the 22nd of November, we will have something solid to compare them to, and the quiet question hanging over the Rayong triple tail will sharpen into a clearer choice between the familiar behaviors of ordinary comets and the more demanding possibilities suggested by this unusual interstellar visitor. When you look back through the modern history of comet watching, you find that 3I Atlas is not the first object to face a storm from the sun. Long before its triple tail appeared in Thai images, other, more familiar comets had already served as test subjects in unplanned experiments, caught in the path of coronal mass ejections and forced to reveal how fragile their tails really are. Among those encounters, one in particular has become almost a textbook example. In 2007, a coronal mass ejection swept past a small, periodic comet named Encke, and space-based cameras recorded something that, even now, looks surprisingly violent for such a quiet patch of sky. In just a few hours, the comet's bright, narrow tail was severed from its head, left drifting behind like a smoke plume cut off at the source. The Encke event is worth holding in your mind because it shows, in slow motion, how a typical comet responds when the steady solar wind is briefly replaced by a denser, more chaotic front. As the coronal mass ejection overtook the comet, the magnetic field carried within the cloud pushed sharply against the plasma environment around the nucleus. Field lines that had been stretching smoothly away from the sun were compressed, twisted, and then reconfigured. The ions tracing those lines were swept into new paths, and the visible tail, which is really just a collection of those ions glowing in ultraviolet light, went with them. To an observer watching the sequence of images, the effect was stark. One frame showed the comet with its normal tail. The next showed the same nucleus, but the tail had become disconnected, left behind to fade as the storm moved on. On Earth, nothing about this looked dramatic to the naked eye. There was no flash and no sudden brightening. The drama lived entirely in the details captured by instruments. Yet for comet science, the lesson was vivid. Tails are not solid appendages. They are flexible tracers of the invisible magnetic field and plasma flow in which the comet is embedded. When that flow is disturbed, tails can be kinked, twisted, or, in the most extreme cases, broken off entirely. After the Encke event, researchers combed back through older observations, finding hints that similar disconnection events had occurred for other comets when strong solar disturbances passed by. Together, these cases built a kind of reference library for what normal responses to storms look like. Several themes run through that library. The first is that ion tails are usually the most dramatically affected because they are made of charged particles that are tightly coupled to the magnetic field. They respond quickly when that field changes. Disconnections, sudden bends, and rapid brightening or fading are common in these parts of the tail. Dust structures, while not immune, are slower to react. The heavier grains that make up dust tails feel the changing environment more indirectly through drag and collisions with gas, so their response is often more muted and gradual. In many past events, the dust tail continues to trail behind the comet in roughly the same way, even as the ion tail is being stretched or cut. The second theme is that once the front of the coronal mass ejection has passed, comets tend to rebuild their disturbed structures. The nucleus continues to emit gas and dust, and the steady solar wind returns, re-establishing a more familiar configuration of fields. Within hours or days, a new tail forms, sometimes quite similar to the original, sometimes subtly altered. From a distance, this can look like a kind of cosmic resilience. Underneath, it reflects the fact that as long as the comet continues to outgas, the environment around it is constantly renewed. The storm does not permanently remove the ability to form a tail. It merely disrupts one particular arrangement of plasma and dust before the system settles back into a new equilibrium. Against this backdrop, the situation of 3I Atlas takes on a more precise shape. The coronal mass ejection, expected to cross its path around the 22nd of November, is not an unprecedented event. It is another instance of the same kind of solar disturbance that once cut the tail from Comet Encke and has brushed past countless other small bodies. We therefore have a baseline expectation. If 3I Atlas behaves like an ordinary comet, we might expect its ion tail to show signs of stress during and after the passage. A kink, a partial disconnection, or a brief episode of fading would not be surprising. The dust tail, meanwhile, might show only gentle changes, perhaps a slight shift in curvature or brightness, as the gas flow feeding it is temporarily disturbed. The third, sunward channel, is where the uncertainty lies. Because such structures are rare, we do not have a thick catalog of past examples to consult. If the sunward tail of 3I Atlas is primarily an ion feature, tied closely to the magnetic field and dusty plasma structures we have imagined, then it may be particularly sensitive to the passing storm. A strong jolt in the local field could scatter the charged grains that currently trace that narrow lane, erasing or blurring it in much the same way that the Encke event tore the main ion tail away. On the other hand, if the channel is anchored more deeply in the dense, possibly planetary fossil nucleus, or if it relies on a robust internal magnetic framework, it may prove harder to disrupt. It might bend, dim, or briefly fragment, only to reassemble along the same general path once the most turbulent part of the coronal mass ejection has moved on. Either outcome will be instructive. A fragile, easily severed sunward channel would reinforce the idea that we are seeing an especially delicate manifestation of dusty plasma structure, beautiful but dependent on a calm background. A resilient channel that survives or quickly reforms would push us toward models in which the nucleus of 3I Atlas plays an even more dominant role, enforcing order on the surrounding plasma in spite of external stress. In that case, the comparison with the Encke event would highlight not just similarities in how comets and interstellar visitors respond to storms, but also the ways in which 3I Atlas stands apart. For listeners lying quietly as they follow this thread, it may help to think of the coming days as a kind of slow-motion experiment with three simple questions. What happens to the familiar dust tail when the storm arrives? What happens to the more volatile ion tail? And what happens, most crucially, to the strange sunward third tail that has defined the mystery so far? The answers will not arrive with a single dramatic image, but with a sequence of careful exposures taken before, during, and after the passage. Somewhere in that sequence, hidden in the changing shapes of faint streaks of light, will be the clues needed to decide whether 3I Atlas belongs comfortably in the existing library of comet behavior, or whether its triple tail will force comet science to stretch its shelves a little wider. When the front edge of the coronal mass ejection finally sweeps past 3I Atlas, nothing on Earth announces the moment. There is no visible flash, no sudden flare in the night sky. The only sign is a subtle change hidden in pixels and spectra, waiting inside files that will be downloaded, calibrated, and quietly compared. In that waiting, the long chain of ideas we have followed so far comes to a single, simple point. The triple tail pattern that began as a strange photograph from Rayong has now been exposed to a real stress test. However the sunward channel responds, it will speak more clearly than any diagram about what kind of object 3I Atlas truly is. One possibility is that the third tail proves to be as fragile as it looks. In this scenario, images taken during and after the passage of the coronal mass ejection show the sunward channel torn, smeared, or simply gone, erased along with disturbances in the ion tail. The main dust tail persists in a softened form, and over time, the more familiar two-tail configuration re-establishes itself. If that is what the data reveal, the triple tail becomes a brief, exceptional arrangement rather than a deeply anchored feature. Dusty plasma structures and magnetic cages would still be part of the story, but they would be cast as delicate sculptures that cannot survive a strong external shock. The case for a dense planetary fossil at the core of 3I Atlas would not vanish, yet it would no longer need to carry the weight of explaining a sunward channel that can outlast storms. A second possibility is more ambiguous. The triple tail might be disrupted by the storm and then reform, not as a perfect copy of its earlier self, but as a slightly altered pattern. The sunward channel could reappear with a small shift in angle, a change in brightness along its length, or a new degree of waviness, like a scar that remembers the direction of the blow. That outcome would hint at a structure that is resilient but responsive. The forces that shape the third tail would be strong enough to reassert themselves after the passing disturbance, yet flexible enough to incorporate some imprint of the encounter. For modelers, this would be a rich case. It would suggest that internal properties of 3I Atlas, such as a compact, conductive nucleus and a persistent local field, work together with the varying solar wind to produce a pattern that can be bent, but not easily broken. There is, however, a more dramatic possibility. In this third scenario, observers find that the triple tail of 3I Atlas passes through the storm with surprisingly little change. The main dust tail reacts in familiar ways. The ion tail may show a kink or a brief disconnection, then heals. Yet the sunward channel remains aligned, narrow, and sharply defined before, during, and after the estimated crossing of the coronal mass ejection. If careful analysis confirms that the timing is correct and that the storm truly swept across the object's path, then a sunward channel that survives essentially intact becomes difficult to treat as a transient, surface level feature. It begins to look instead like the visible trace of a robust magnetic architecture tied directly to the dense body at the center. In that light, the usual label of comet starts to feel a little thin. At this point, the phrase something truly unfamiliar becomes more than a poetic flourish. For a viewer who has followed both the grounded mysteries and the more speculative hypothetical nightmare stories on this channel, two broad classes of explanation naturally step forward. One is the planetary core hypothesis, in which 3i Atlas is the exposed heart of a shattered dwarf world, carrying with it the ability to generate and sustain strong local fields that organize dusty plasma even under stress. The other is the more unsettling idea that has floated through earlier speculative episodes, the thought that a persistent triple tail structure might be the byproduct of controlled activity from an artificial object, a kind of engine signature built to remain stable even when the solar wind turns violent. In Mode GM, our task is not to dramatize that second possibility, but neither do we have to pretend it has never been imagined. If the sunward channel shrugs off a coronal mass ejection with ease, some viewers will inevitably remember scenes from previous videos where light curves and odd accelerations were discussed in the context of hypothetical spacecraft. The disciplined way to respond is to ask what kind of numbers each explanation would require. How strong would a natural magnetic field need to be to guide charged grains through a storm without losing coherence? How dense would a planetary fossil have to be, and how would that density show up in its brightness and outgassing behavior? What sort of engineered system, if one were truly present, could produce an exhaust pattern that imitates those natural signatures so closely that it is indistinguishable in our current data? These questions pull the discussion back toward measurement. A planetary core that can support a stable triple tail through a storm would set lower bounds on an internal density and conductivity. Models would need to show that such a body can reasonably arise from the breakup of a dwarf planet in another system, and that its interaction with the solar wind can produce the observed patterns without violating conservation of energy or known limits on field generation. An artificial object, if entertained at all, would face even stricter tests. It would have to fit inside all of the same observational constraints that apply to natural models, leaving no excess heat, no sharp, non-gravitational maneuvers, no spectral lines that obviously betray technological materials. In practice, the absence of such anomalies tends to favor the planetary fossil scenario, not because we are refusing more imaginative answers, but because the simplest explanation that fits all the data is usually the most useful starting point. Yet even if the balance of evidence continues to lean toward a natural origin, the idea that 3i Atlas could carry a magnetic architecture strong enough to preserve a sunward tail through a solar storm is already a stretch beyond ordinary comet lore. It nudges us toward an expanded category of objects, small bodies that behave half like comets and half like exposed planetary remnants. In that expanded category, The line between normal and unfamiliar is no longer drawn between natural and artificial, but between shallow and deep histories. A fluffy nucleus remembers only the outer layers of a system. A planetary fossil remembers its interior. If the triple tail survives the storm, it will suggest that we are looking at the second kind of memory, written not in craters and mountains, but in the way dust and plasma are disciplined into shape. For listeners resting in the dark, this is a good place to let the two images coexist without needing an immediate verdict. On one side, there is the grounded, quietly dramatic picture of a broken world's core passing through our neighborhood, its hidden structure revealed by the way it holds its triple tail together under pressure. On the other side, there is the more speculative silhouette of a constructed object, a possibility that remains on the horizon of thought rather than in the center of the frame. You do not have to choose tonight. You can simply watch how the data unfold, knowing that any explanation able to survive the combined weight of observation and physics will be interesting enough in its own right. As this section draws to a close, what the coming storm really offers is not a final label for 3i Atlas, but a sharper lens. By seeing how the triple tail responds to a sudden change in its environment, we learn how much of its behavior is rooted in fragile surface effects and how much is tied to deeper properties. In the chapters ahead, we will step back from the flow of particles and the push of solar storms and think about what it means, more broadly, to live in a galaxy where fragments of distant worlds pass through our sky. The triple tail, whatever its ultimate cause, is an invitation to that wider reflection, a reminder that even a small point of light on a detector can carry stories that stretch from the hidden interiors of shattered planets to the patient curiosity of observers watching, quietly, from a darkened Earth. By the time light from 3i Atlas reaches our telescopes, it has already traveled for years across interstellar space. That simple fact turns the object from a local curiosity into a kind of messenger. The dust, gas, and possible planetary core at its center are not native to the solar system. They were assembled somewhere else, under a different pattern of starlight, in a planetary system that may no longer exist in the form that first gave birth to this fragment. When you look at the triple tail on a processed image, you are not just seeing what 3i Atlas is doing tonight. You are seeing the late echo of events that unfolded far away and long ago, written in the language of density, composition, and magnetic habit. In our own system, we have learned to think of the Oort cloud as a deep reservoir of icy remnants, a spherical halo that may extend tens of thousands of astronomical units from the Sun. It is a place where comets wait in the dark, disturbed every so often by passing stars or slow tides from the galaxy. Many of the long-period comets that sweep through our skies likely began their journeys out there, nudged onto paths that finally carried them inward. Beyond our cloud, other stars almost certainly host similar shells of debris, their own quiet swarms of frozen fragments. Every time a planetary system is stirred violently, some pieces are not just rearranged, they are thrown completely free, placed on orbits that no longer belong to any single star. 3i Atlas is part of that larger traffic, one of the small bodies that have slipped the gravitational nets of their home systems and now drift through the galaxy as unbound messengers. The triple tail we have been following is, in this sense, a kind of handwriting from deep time. If 3i Atlas is indeed a planetary fossil, then its dense nucleus once sat deep inside a layered body, Above it might have been a mantle of rock or ice, perhaps an atmosphere, perhaps a surface where chemistry unfolded in ways we can only guess. Collisions, orbital instabilities, or the slow evolution of its host star eventually stripped those layers away. What remains is the core, compact and tough, carrying in its arrangement of elements the record of that system's early heat, its distribution of metals and volatiles, its particular way of building small worlds. When the core passes near our Sun, those properties are revealed indirectly in how the nucleus resists erosion, in how it shapes dusty plasma into channels and cages, in how it responds to storms. Each bright filament is a translated sentence from that older story. We already have a hint from One Eye, Oumuamua, and Tuapkai Borisov that interstellar visitors do not all look alike. One tumbled through with an elongated shape and a puzzling non-gravitational acceleration. The other looked more like a textbook comet with a broad coma and ordinary tail. 3i Atlas, with its stubborn triple structure, would extend that small catalog of examples in a new direction. Together, these objects sketch the rough outline of a population we have only just begun to sample. They suggest that planetary systems do not simply produce one kind of leftover. They eject shards of many kinds, from fragile aggregates to compact cores, and those shards now wander among the stars, occasionally crossing the light of a telescope in a quiet observatory far from their birthplaces. From a scientific perspective, the importance of such visitors is practical as well as poetic. We cannot send missions to every distant star that hosts planets. Even with optimistic technology, that kind of exploration remains out of reach. But fragments like 3i Atlas bring pieces of those systems to us. Their spectra can reveal unusual mixtures of gases. Their dust can hint at mineral recipes that are rare or absent in our own comets. Their internal strength and magnetic behavior can tell us whether other systems tend to build planets with dense metallic hearts, thick icy crusts, or something in between. Each interstellar comet is a sample return mission that the galaxy has already paid for and launched long before we learned how to recognize it. This point of view puts the triple tail in a slightly different light. Instead of asking only why an object here and now is defying parts of our standard comet physics, we can also ask what its behavior says about the distant environment in which it formed. A nucleus capable of sustaining a stable sunward channel under the push of radiation and the passage of a solar storm implies a certain robustness. It suggests that the world which once housed this core lived under conditions that favored differentiation, magnetic activity, and a rich inventory of volatiles trapped in deep fractures. It might mean that the system where 3i Atlas was born had a history of intense collisions, enough to strip away outer layers, or that its star went through phases that made the survival of compact cores more likely than the survival of fragile, fluffy bodies. These are not firm conclusions, but grounded speculations that tie the behavior of one small traveler to the broader patterns of planetary architecture across the galaxy. For someone listening in the dark, it can be quietly comforting to imagine this continuity. The particles in the triple tail, now being reshaped by the solar wind near our sun, were once buried inside a distant world. They may have spent hundreds of millions of years locked in place, following slow cycles of heat and cooling, before some instability tore them free. Their journey between the stars may have taken even longer, centuries or millennia of drifting through thin starlight, untouched by any strong wind. Only now, for a brief interval of months, are they being lit brightly enough for us to see, arranged into shapes that carry clues about where they came from. When the passage is over, the tails will fade, the dust will disperse, and Three Eye Atlas will continue outward, carrying whatever remains of its core into deeper night. In that sense, calling this object a messenger is not just a metaphor. It really does bring us information that could not have arrived any other way on human timescales. The message is not a coded signal in the science fiction sense. It is a pattern of behaviors, a set of constraints on density, composition, and field strength, a record of how one fragment of a long lost world reacts under the specific conditions of our solar wind and sunlight. The challenge for us is to read that message carefully without forcing it into stories that are more familiar than accurate, and without ignoring the parts that stretch our intuition. As this section of the journey settles, a gentle question lingers. How many other planetary fossils are moving through the dark between stars, carrying their own complex histories, and how many of them will pass close enough to a curious civilization to leave signatures as striking as the triple tail of Three Eye Atlas? In the next part, we will turn our attention back toward Earth to the telescopes and quiet observers whose sensitivity made this particular messenger visible at all, and ask how our growing ability to notice such subtle structures is changing the kinds of stories the universe can tell us while we drift toward sleep. If the triple tail of Three Eye Atlas feels like a message from a distant past, the way we first noticed it belongs very much to the present. A century ago, even the most dedicated astronomers would have struggled to see more than a broad, luminous sweep where Rayong's image now shows three separate structures. Glass plates, hand-guided mounts, and delicate emulsions were good at capturing the overall glow of a comet, but they were less forgiving of faint, narrow features and subtle changes from night to night. Much of what happened in the inner regions of the tail was simply washed out, a blur of light that hinted at complexity without resolving it. The quiet revolution that makes Three Eye Atlas feel different is not only in the sky. It is on the ground, in the way cameras, software, and networks of observers have changed what looking means. At the core of that change is the modern small telescope. Instruments not much larger than those used in amateur backyards now carry sensitive digital detectors that can register individual photons with remarkable efficiency. In places like Rayong, a modest mirror, carefully aligned and guided, can feed light into a cooled sensor that keeps recording while the night drifts past. Each exposure might last only a minute or two, but software can stack dozens of them, aligning the faint dot of Three Eye Atlas and letting random noise cancel itself out. Structures that would once have been invisible begin to emerge. A faint, sunward streak that would have vanished into the grain of a film plate becomes a measurable feature, one that can be traced, quantified, and shared. Satellites and large survey telescopes play their part too, discovering interstellar visitors like Three Eye Atlas and mapping their paths with enough precision that smaller observatories know where to look. But the detailed story of the triple tail belongs to a different scale. It lives in the images taken by patient observers in Thailand, in Europe, in the Americas, and Australia, each working with instruments that fit in modest domes or even roll-off roofs. It is their willingness to spend long nights collecting and processing data that turns a catalog entry into a living puzzle. Without them, Three Eye Atlas would pass through the inner solar system as a brief uptick in brightness on a survey plot. Interesting, but anonymous. With them, it becomes a case study in how subtle structures can reveal deep properties. There is also the way these observers now talk to each other. A few decades ago, a strange tale in one observatory's image might have taken weeks to become widely known, traveling by letter or printed circular. Today, a processed frame from Rayong can be posted within hours, annotated and discussed by professionals and amateurs alike. Someone in a high-altitude lab can download the same data, apply different filters, and see whether the third tale survives. Someone else can cross-check with spectra, looking for signatures that might hint at unusual gases. Channels that specialize in explaining new results to the public can pick up the story, translating careful measurements into narratives that carry both wonder and rigor. In that sense, the telescopes that have changed the game are not just the ones in domes. They are also the ones embedded in laptops and handheld screens, turning individual observations into shared experiences. This interconnected way of seeing means that anomalies no longer belong to single sites. The triple tail of 3i Atlas is not just the Rayong feature or the Thai anomaly. It is a global object in the data sense, observed from many longitudes, under different skies, with the instruments of varying size. When multiple observers report the same sunward channel, when independent reductions reveal the same narrow structure, the confidence that it is real grows. At the same time, the diversity of perspectives allows for a richer test of models. A faint kink seen in one set of images can be checked against another. A temporary brightening near the nucleus can be compared with solar wind conditions recorded by spacecraft. Each telescope contributes a piece to a mosaic that is larger than any single field of view. From the point of view of someone drifting toward sleep with these ideas, there is something quietly reassuring about this networked vigilance. It means that the universe does not depend on any one observer's clear night to reveal its more delicate patterns. If clouds roll in over Rayong, there may still be a clear sky over a hillside observatory in Spain or over a small concrete pad in Arizona where another telescope is tracking the same coordinates. The data stream is not perfectly continuous, but it is resilient, stitched together from many lives and routines. Some observers are students, fitting exposures between classes. Some are retirees who have turned their back gardens into small research stations. Some are professionals on mountaintops. All of them, knowingly or not, are participants in the same slow unfolding of 3i Atlas's story. The technology behind their work, with its cooled sensors and image processing algorithms, can sound dry on paper, yet its effect is very human. By lowering the threshold for what can be seen and recorded, these tools have brought the frontier of subtle structure within reach of more eyes. A feature like the triple tail, once the exclusive domain of large observatories and rare photographic luck, can now be followed by a loosely organized global community. That community, in turn, feeds channels of interpretation, from technical preprints to gentle, sleep-friendly documentaries, all built on the same foundation of shared, carefully treated photons. The instruments that change the game are, in this sense, empathy machines as much as measuring devices. They allow people who will never meet to look at the same tiny streak and feel the same quiet curiosity. This shift matters for more than sentiment. It changes the kinds of questions we can ask. When sensitive telescopes are distributed widely, we can look for patterns that emerge only over time and across many sites. We can ask how often features like the triple tail appear and vanish, whether they correlate with particular kinds of solar activity, whether they are more common in interstellar visitors than in homegrown comets. The data needed to answer those questions do not come from one spectacular night. They accumulate in small increments, in archives that can be revisited long after 3i Atlas has faded from direct view. The telescopes that changed the game are the ones that make such accumulation possible, quietly, night after night. For Dreamy Stargazer, and for listeners who keep returning to its soft-spoken tours of cosmic puzzles, this era of enhanced seeing opens a particular kind of space. It allows stories like that of 3i Atlas to be told not as isolated events, but as chapters in an ongoing dialogue between human perception and the sky. The triple tail is not just a picture to admire once and forget. It is a phenomenon that can be revisited, reinterpreted, and tied to future discoveries as new interstellar objects arrive and new instruments come online. The same way faint galaxies once transformed from smudges into spirals under better optics, so too may the strange structures of cometary tails evolve in our understanding as detectors become more sensitive and analysis becomes more collaborative. As this part of the journey closes, you might imagine the Earth at night as a dimly glowing sphere, speckled with tiny islands of light where telescopes are tracking. On one coast, someone is taking a last set of exposures of 3i Atlas before dawn. Half a world away, someone else is just opening a dome for the evening. Between them, data will flow, images will be stacked, and the triple tail will be watched for as long as it remains visible. The object itself will move on, indifferent to our instruments, but the story we extract from its passage depends deeply on this global tapestry of small mirrors and patient minds. In the next and final section, our attention will turn inward to the quiet act of waiting with such data and to the way that watching a storm-tested, triple-tailed messenger drift back into darkness can change how we think about our brief role as observers in a very large, very old universe. By the time the story of 3i Atlas reaches this point, the object itself has already moved on. It continues along its open path, slipping gradually out of the inner solar system, trading the steady brightness of our sun for the thinner light of more distant space. The triple tail that once seemed so sharp in Rayong's images will fade, first below the reach of small telescopes, then below the threshold of the larger surveys. Nights will pass when observers point their instruments elsewhere, toward new comets, new transits, new patches of empty sky that may or may not contain another interstellar visitor. In the archives, though, 3i Atlas does not leave. Its frames, spectra, and light curves remain, quiet files on distant servers, waiting for anyone who wishes to open them and ask again what kind of body could have carved three such distinct channels into a river of sunlight and plasma. In that sense, the experiment the Sun conducted with its coronal mass ejection never really ends. The immediate encounter, somewhere around the 22nd of November, produces a finite sequence of data. Yet the interpretation of that sequence is an ongoing act. As new models are developed for dusty plasma, as our understanding of planetary cores and magnetic relics grows, the old images can be reprocessed and reinterpreted. Someone years from now may download the Rayong data again, apply a better algorithm, and recover subtle ripples in the third tail that we barely noticed. Someone else may use future interstellar objects as comparison cases, finding patterns in how such visitors respond to storms. In this slow way, the triple tail continues to participate in our science long after the light that first revealed it has scattered into the background of memory. For Dreamy Stargazer, and for you listening in the dark, 3i Atlas becomes part of a more personal archive as well. It joins the quiet roster of objects whose names come back in later episodes, threads that weave through different stories. Perhaps you will hear it mentioned again in a discussion of magnetic relics, or in a gentle comparison with some later visitor whose tale behaves in a more ordinary way. Perhaps you will remember when a host points out a faint asymmetry in another comet's coma that once there was an interstellar traveler whose sunward channel refused to be ignored. Little by little, these memories accumulate, not as a rigid curriculum, but as a constellation of impressions that make the night sky feel less abstract. Each strange feature you learn about becomes a landmark, something you can carry with you even when you are far from any telescope. There is a quiet comfort in knowing that our role in this story is limited but real. We did not launch 3i Atlas from its original system. We did not choose the moment when the sun would send a storm across its path. Our part was to notice, to measure, and to reflect. Observers in Rayong and around the world aimed their mirrors at a small set of coordinates, let photons fall onto sensitive sensors, and shared what they found. Modelers turned those findings into equations and simulations, exploring which combinations of density, field strength, and dust behavior could reproduce the triple tail. Storytellers, in channels like this one, shaped the whole process into something you could fall asleep to, turning hard questions into soft-spoken narratives that wrap around your thoughts without demanding that you stay awake to the end. In the larger scale of the galaxy, this may seem like a very small contribution. Stars burn for billions of years. Planetary systems rise and fall. Entire families of interstellar objects will pass through the void, whether or not a young civilization around a yellow star happens to be watching. And yet, from our vantage point, this brief attention matters. For a thin slice of cosmic time, one fragment of a broken world crossed our sky and found itself lit by instruments and curiosity rather than by indifference. We traced its triple tail, we watched it face a storm, and we allowed ourselves to wonder what its resilience or fragility might say about the deep histories written inside small, wandering stones. As you feel your body growing heavier against the bed or chair, you might let the image simplify. The equations and magnetic cages can fade to the background. What remains is a small point of light moving through a larger darkness, leaving behind faint threads that curl and straighten in response to a distant star. Around that point of light, scattered across Earth's night side, are many other small points where people once watched, where domes opened and screens glowed. For a little while, their attention and yours intersected with the path of 3i Atlas, and together you formed a kind of lens, bringing its subtle structure into focus before letting it drift away again. You do not need to hold the details tightly as you fall asleep. It is enough to know that the universe is full of such passing experiments, most of them unseen, a few of them caught in the thin beam of human awareness. Somewhere beyond the reach of our current telescopes, other fragments are moving inward, carrying their own complicated interiors and their own potential surprises. Some will look ordinary. A few may bend our expectations in new directions, just as the triple tail of Three Eye Atlas has done. Each one will offer another chance to ask calm, patient questions about how matter behaves under unfamiliar conditions, and another chance to feel that particular blend of smallness and connection that comes from watching events far beyond our control. For now, though, the best thing you can do is rest. Let the idea of Three Eye Atlas recede, like a dim star sliding behind the edge of a window. Let your breathing slow to match the quiet pace of an object coasting outward on its long, unhurried arc. Somewhere, data continue to be stored, models continue to be adjusted, and the galaxy continues to move in its vast, indifferent dance. Here in this room, your part of the work is finished for tonight. You have listened, you have imagined, and you can gently set the puzzle down. The universe will still be here when you wake, and there will always be more light to catch, more tales to trace, more questions to approach with the same steady, curious calm.